All right, so, ladies and gentlemen, let's go ahead and let's start putting some things formally together. More specifically about work and power. Now, within this unit, we really talk about work, power, and energy. Okay? So we will eventually be building towards a conversation about energy, which is a little bit different because we haven't really talked about energy in this context yet this year. Why are we doing this? We need to build up to a point where we can start using an energy approach to solving problems. There are some instances in which if we were to try to take Newton's laws or other aspects, other avenues, it would make it a very difficult way to try to solve something. Like take, for instance, an example where you might have a whole bunch of forces. And it might not necessarily even be possible to measure all those forces and figure out what's happening from a direct Newton's law standpoint. Okay? Or, okay, what happens, and we'll talk about this kind of in the second bullet, what happens if we don't have constant amounts of forces? Because the reality of nature is that's how certain things happen. Okay? Sometimes we need to be able to take what we call an energy approach, meaning that instead of focusing on the forces, acting on the mass to figure out the acceleration and things like that, we can kind of do that a little bit differently, knowing some other types of information. Does the energy approach work for everything in this universe? I mean, we could try to do certain things. But again, we're just trying to add another tool to our toolbox as to these are some scenarios that we can dissect from an energy perspective. Okay? And again, as we just stated, that particular approach is very helpful when we have instances of what we call a non-constant force. Because if we were to do Newton's laws, where let's do the kindergarten version, F equals ma, and we know the net force acting on something is 10 newtons, well, that means that it has to constantly stay at 10 newtons, even though the object would be accelerating. And often that's actually pretty hard to do, to get a force to be constant like that. So one of the things that this energy approach is going to be able to do is we're going to be able to build up to situations that do not have a constant amount of force. So kinematic equations, Newton's laws, we're all assuming there's a constant amount of force and a constant acceleration. And that isn't always the case. So I want you to imagine for a second, okay, we have a very simple scenario. We have an eraser that's just sitting on some sort of horizontal surface, and we are going to apply a force on that eraser. Now, as per the diagrams in A, B, and C, the only thing I want for us to imagine for a moment is we're going to change how we apply that force. So whatever the quantity of force is, let's call it relevant, but we'll keep it constant across all three diagrams. We want to try to figure out which of these forces, based on how they're displayed, would do a different amount of work. Okay? And I know we don't really know the relation between work and force, but we're kind of putting it together here. So let's do this. Let's imagine that that eraser was stationary, and let's kind of go back to maybe a Newton's law type problem. Which of these forces would yield the greatest horizontal acceleration? I think all of us would agree what? B. Why is it that B gives us the greatest amount of horizontal acceleration? That, okay, and when we put that, and that together, it makes a happy little right triangle that we can dissect and we can go ahead and say, okay, all right, that more of that force's horizontal component, okay, would be able to apply that towards some sort of acceleration. Whereas in A, we still would have the right triangle that Jack was air drawing over here, but less of that force would be applied in the horizontal direction, so we wouldn't get the acceleration out of that. And C, if we were to push directly down onto it, is that going to provide any sort of horizontal acceleration? No. Okay? Now, we're assuming, again, if the magnitudes of these forces are equal, then the force applied in image B is going to do more to move the eraser, and the force in image C doesn't do anything at all. Okay? Now, one of the things that this goes to show us is we call it the vector nature of this applied force. Okay? It's something that we have to consider. What do we mean by vector nature of a force? We mean the angle at which that force is relative to, as we're going to find out, something. Okay? Not other forces and not necessarily another axis, at least specifically. Okay? So we need to know the vector nature of that force, and we also need to know how far that force moves the object. Okay? So there's really two things that we need to figure out as we're trying to figure out the amount of work being done. Okay? So let's now jump to the formal equation just to go ahead and put this together. The work done, work abbreviated by capital W, and by the way, we will have a unit that you've already seen from your lab that is also capital W in this unit. I do want to emphasize there is a difference between the variable W and the unit W. One is a part of the mathematical equation, the other one is what comes directly after some quantitative values. So just be careful of it. And they do mean two totally different things. But the work done by an object, and work done on an object by an agent exerting a constant force on the object is the product of the component of the force and the direction of the displacement and the magnitude of the displacement. Good, everybody's got that. We're ready to move on, right? Wait a minute. No. Okay? One of the things that I want you to consider about this, one thing that we need to change our mindset about, when we focus on the calculation of work, we focus on an individual force at a time. Why is that a shift? Because in Newton's laws, we considered all of the forces that acted on it to some sort of acceleration of that object. Now, we're focusing on how each individual force is going to impact the amount of work being done on it. So, can we still have multiple forces acting on an object? Absolutely. But know then that each of those forces can do a different amount of work. Okay, at least according to what our definition is going to be. So that's the force, and I will say that's kind of the F cosine theta piece of it. That is helping us to figure out what that is. I need to further explain what this angle is, so just kind of hang tight. That's going to be one of the last things that we do. But we need to know, well, what's the quantity of force? The D, and this might be a little bit misleading, okay? It is going to be the magnitude of the displacement. And I want you to write yourself a happy little note somewhere near that equation in your notes. That the D stands for the magnitude of the displacement. Do not care whether it is going left, whether it's going right, whether it's going up, whether it's going down, whether it's going east, okay? Whether it's going that way. Doesn't matter. Okay? It is just the magnitude of that. Care not about direction. We do care about quantity. Now, the one thing that students typically have some difficulties with, and we're going to address it today, is that theta. Normally, that angle that we've done has just been measured with respect to, more often than not, the x-axis. We've had some instances already where it's been measured with respect to the y. That theta in this equation has nothing to do with the x or y axis. So what does theta actually mean in this? It is, and I absolutely want everybody to be writing this down in your notes, it is the angle between that specific force. It is the angle between that specific force and the displacement. It is the angle between that force and the displacement. Okay, I'm going to get to an example. I believe it's on the next slide that might kind of help us a little bit more with that concept. Is it there? Yeah, we'll do it there. Okay, so let's take a little bit of a step back to image C, okay, where we're pushing down onto our eraser with some quantity of force. For two reasons, we should be able to answer why that force, according to the scientific definition of it, is doing no work on that eraser. What's the first way in which we know we should be able to say? It's not moving. There's not going to be any displacement. That force is not responsible for any sort of displacement. So if there's no displacement, we know that. There's another thing as well. even if that eraser was already moving, okay, what is the angle between that force, which is pushing down, and something that only really has an option to move horizontally? What would that angle be between the force and the displacement? 90 degrees. Everybody do your calculators. If you don't already know your unit circle, the cosine of 90 degrees equals, who's saying? Nothing. Okay? So a force that acts perpendicular to the displacement is never going to do any work. Now, does that mean that anything that pushes down or up does no work? Absolutely not. We always have to be considering what is the direction of the displacement. Okay? So anytime we have a force that's perpendicular to the displacement, the amount of work is going to be 0. I'm going to add one thing to this kind of free body diagram that's done down here. Okay? We have some sort of a force that's being applied at an upward angle, okay, above the positive x-axis. We have weight, we have normal force that I know are being notated a little bit differently. Let's go ahead and let's add a frictional force according to our labels. Again, I know that there's different notation up there than what I typically use for weight and normal force. That's okay. So, let's take a look at that free body diagram. So the weight, center of mass pulling straight down, we're told that this is being displaced to the right. What is the angle between the weight and the displacement? We'll ask again. Weight's pulling down, displacement's going to the right. What is the angle between the weight and the displacement? It's 90 degrees. How much work does the weight do in this example? 0. Okay? Because ultimately it doesn't matter about force and displacement because we're multiplying it by the cosine of 90, which would give us 0. 0 times anything gives us 0. In the same fashion, in this example, look at the normal force. Okay? Contact surface pushing up, displacement is to the right. What is the angle between the normal force and the displacement in this example? 90, which means the amount of work is 0. Okay? Now, we'd have to know some more information if we actually wanted to calculate it, but let's just take a look at this force. Let's just call it an applied force. Okay? If this force is, let's say, at an angle of 45 degrees and we had a force of, I don't know, 10 newtons, well, we could figure out the amount of work being done because we would know the force, we'd know the angle, but we always have to check this. Is that angle measured with respect to the displacement? We would say yes in this case. Okay? It's being displaced to the right. Okay? The angle is being measured above the positive x-axis. Okay? So that would be an angle. So if we said that was 45 degrees, we'd have to know the force, we'd have to know the displacement, and the angle with respect to that. Yes, ma'am? It doesn't. That's a good question. Okay, it's the same point. It doesn't really matter if we measure from the front edge of the object, the back edge of the object. It just, as long as we measure that from the consistent point for this type of object, that would be fine. But one more thing. Can I just do one more thing and then I'll get to it? Actually, let me do 2 more things and I'll get to your question. Let's pretend for a moment that this force is actually not at an upward angle, but now it's going to be directly to the right. So, what is the angle between the force and the displacement? If the force is pointing to the right and the displacement is also pointing to the right, what is the angle between 2 things pointing in the same direction? 0 degrees. Okay. Is there going to be an amount of work being done by that force? Absolutely. Okay. For those of us that are really good with our unit circle, the cosine of 0 degrees is 1. 1 times whatever is there. That's going to give us our maximum amount of work being done. Okay. Last one, and then I will get to your question. Okay. Frictional force, as per this diagram that I have drawn in. Frictional force points to the left. Displacement points to the right. What is the angle between things that point in opposite directions? 180 degrees. Cosine of 180 is, for those that know it, -1. Okay, times everything that would be there. According to our definition, that would give us a negative quantity of work. I know right now, negative quantity of work doesn't necessarily make sense, but it is what we get. We'll explain what that also may mean in a minute. Question? Well, when you walk, there's other things that's kind of going on. In terms of your weight pushing down, okay? And if you are moving horizontally, that specific aspect of the forces acting on your body, if you're the one walking, that your weight is not doing work in that instance. Okay? Are there other things that are going on? Yes. And there are other forces that could be doing work, just not that one specifically in your example. Okay? And I'm going to get to some of the examples of like walking up steps and doing things kind of like what we had talked about from our lab, and we'll kind of get to some of those examples in a minute. So kind of two things I want to do is take away, and then I'll absolutely get to your question. Okay? One, we have to consider individual forces. Okay? Notice how not once have we ever talked about the sum of forces, adding everything up together. It's totally different than what we did from Newton's laws of motion. And the thing that students usually have a little bit of trouble with, and at least maybe the initial stage, is the concept of that angle. So here's what would happen in a problem. You're either going to get that angle along with the diagram, well that should help with at least one of those forces, or we might need to figure out what's going on. And more often than not, if you're not given an angle, you have one of three choices. It's either 0 degrees, meaning it's pointing in the same direction as the displacement, it's going to be 90 degrees, which means it's perpendicular to that, or it's going to be 180 degrees, it's pointing in the opposite direction to that. So just kind of keep that in the back of your brain. Question? When we get to the mathematics of it, yes, we would be doing a separate calculation for each force, at least those of you be asked to find. So, correct, it wouldn't just be what's the total work being done by the object with like 8 different forces acting on an object. Okay, it's going to be what is the work done by the weight, what's the work done by attention, you know, what's the work done by, and they will, depending on the application of that problem, they will have some different answers. And that's okay.
Would it be like W sub, like
you can, in terms of the notation of that, when we get to like the forces, I know this is a different free body diagram, you know, but let's say we were talking about the weight, which was the question I just asked, you know, we can then go ahead and just notate that. That also helps us to identify, all right, we're talking about the weight, okay, or we're talking about an applied force or a frictional force. I think that that designation helps. I wouldn't put that designation on the work, just this would be your identifier that that's the force that we're focusing on. Okay, all really good questions. Are we good? Okay, the sign of the work. Okay, and this is ultimately what we're going to build towards. And we're not ready to have that discussion today, but I am going to introduce the concept here. Okay, the sign of the work depends on the direction of that force relative to the displacement. Work is going to be positive when the component of that force is in the same direction as the displacement. Work is going to be negative when the component of that force is opposite in the direction to the displacement. I wouldn't be doing my job as your physics teacher if I didn't try to confuse you. So, this last bullet here at the top of our slide is something that gives people some headaches. Okay, let's figure out why. When we talk about lifting objects and lowering them down, okay, I actually want to do that bullet as the last thing, okay, so we can kind of understand it. Let's say that you're just simply curling an object. You have a big bar you're going to curl up. You're applying a force, so we'll focus on the applied force. What direction do you have to apply a force to lift the weight? It's not a trick question. Up. What is the direction the weight goes? Up. Okay? So, in that situation, we are applying a force in the upward direction. It's going up. What is the angle between the force and the displacement? It's 0 degrees. Again, why? We're pushing up. It's going up. The displacement is up. What is the angle between two things pointing in the same direction? 0 degrees. Okay? Now, if you have good form, for a brief moment, you hold that weight at the elevated point that you've lifted it to. Are you doing work when you hold the weights there? If I stood here all day, and this was an actual dumbbell or bar or something we had, am I doing work by holding the bar there? but I'm applying force. There's no displacement. I'm not doing work. Am I spending energy? I'm applying force. Not doing work. Okay? This is the one that gets people. And then lower it back down. What is the direction of the force that you apply? Before you say something, think for about 10 seconds. You lifted some weight last class. And you lower it back down. What is the direction of the force you apply? Right? It is still up. You are lowering it down in a controlled fashion, aren't you? You're not just dropping it. You're not just letting it go. You're still pushing up on it. And what's the direction of the displacement? Downwards. Okay? So what is the angle in that problem between the applied force, that's in an upward direction, and the displacement, which would be in a downward direction? 180 degrees. Okay? Now, understand that I have framed your thinking of what I just asked you only off one of the forces acting in that scenario, just the applied force the whole time. Okay? The applied force to lift, the applied force to hold, the applied force to lower back down. If we focused on the weight, it would be a totally different scenario. Okay. So, if we're focusing on the weight, the force, okay, that is pulling that back down towards the surface of the earth, okay, or the center of the earth, okay, when we lift it up, well, the weight's pulling it down, but the direction of the displacement is up. Okay, we're going to focus on that force. Okay, again, just know that we would have to make some other considerations depending on other forces we do. So when you lift an object, I know the weight is negative, but the work done by the person is positive. Okay? It just depends on what force we focus on. This middle bullet is really what ties it all together, and where we're going to go over the next couple of classes. Work and why it's so important. Work is going to be a positive quantity if we are transferring energy to the system. Okay? We'll define what a system is. We'll talk about what it is. Okay? But work is all about energy transfer. Are we adding energy to a system, or are we removing energy from a system? Okay? Work is going to be negative if energy is transferred from the system. And lastly, because we've been talking about work all this time, and yes, it is a force multiplied by a displacement, we take the units for that, and it would be a derived unit of newtons times a meter, or the Newton meter. But we don't just leave it in that. We actually give it its own special name. We call it the joule. Okay, which will be abbreviated as the capital J. So when we are calculating an amount of work being done, okay, that is going to be a joule of work. Okay, so let's go ahead. We're going to go to our sample problem packet. We're going to do a couple of quick things here in the sample problem packet. So here we go. A man cleaning a floor pulls a vacuum cleaner with a force of 50 newtons at an angle of 30 degrees with the horizontal. Okay, calculate the work done by the force on a vacuum as the vacuum is displaced by 3 meters. Okay, we have two different forces at which we are going to, actually 3 different forces of which we're going to calculate the work being done. But what do I think is a good place for us to start? Draw a free body diagram. Okay. So we have our vacuum cleaner. That is the object that we have. We have some sort of applied force, okay, that's pulling it in an upward direction. We have the weight, okay. We do have the normal force. I know we're not asked about it or really told about it here. Let's put in friction in here because I want to just have the discussion because we're going to get to that point soon anyway. Probably not going to be a whole lot of friction between the casters on this vacuum cleaner and the floor, but it's not something that we can necessarily ignore. So part A, we're going to calculate the work done by the force on the vacuum, meaning the applied force, as it's displaced by 3 meters. So work equals force times displacement times the cosine of theta. Okay, and as Alyssa kind of pointed out, I think it's necessary, it might be a good thing for us to do. Since we're focusing on that, let's notate that as the applied force. Further driving the point home, it's the individual force that we are focusing on. Okay, so pretty simple pluggy chuggy. We know that that force is going to be 50 newtons multiplied by the displacement of 3 meters, all multiplied by the cosine of what is the angle between the applied force and the displacement? It is 30 degrees. And maybe I got a little bit ahead of myself over here. Might not be a bad idea. Out to the side, you can't add it to the actual free body diagram because it's not a force. Maybe labeling the direction of the displacement might be a good visual for us to see, all right, we're comparing our applied force in this case with that displacement. Please make sure that your calculator is in degree mode. Now that we have the glorious return of some trig functions. And Carter, when you got a good answer, let me know. 129.904. Yes, but no. Okay, yes, Newton meters would be the derived unit for this, but we're not going to express it as that. It's given a special name. Starts with J, ends in ool. There you go. Joules. Good. Okay. 129.904 joules. All right. Any questions? Does that seem pretty easy? Okay. Let's go on to part B. The work done by the normal force. So normal force times displacement times the cosine of, wait, hold on a minute. How do we find the normal force if we don't know what the weight of this is going to be, or the mass of our vacuum cleaner, or any other? What do you mean it doesn't matter? What is the angle between the normal force and displacement? 90 degrees. Cosine of 90 degrees is 0. 0 times displacement times normal force. It's still 0. Here's what I want you to do. If we come across those scenarios, your solution, I'm okay with you doing this, theta equals 90 degrees. Therefore, the work is going to be 0 joules. That would be a sufficient answer for this. Hey, guess what? When we talk about the gravitational force here, the weight of this in part C, okay, work equals, okay, the weight times d times the cosine of theta, but in the same fashion, okay, we know that theta is going to be equal to 90 degrees, and therefore, work is going to be 0 joules. And that is perfectly fine. It wasn't asked here, but if we did know a quantity of frictional force, could we find the work done by a frictional force? Yes. Okay. Maybe to kind of come full circle with something we were saying earlier, the work done by this applied force is adding energy to this system, because if this vacuum cleaner started at rest and we start pulling on it, is it going to start picking up what we'll call kinetic energy? Absolutely. That's adding energy to the system. Now, friction, on the other hand, we know what friction does. Friction is going to reduce the energy in the system. Anytime we talk about friction, what does it generate as a byproduct? A form of energy. Okay. So, we weren't asked about it here, but okay, what is the angle between frictional force and displacement? Should be 180 degrees. Okay? Therefore, it's going to be a negative amount of work if we were asked about that in this example, but we didn't. Questions on A? Okay, B. Mike, a man with a mass of 80 kilograms, walks up and down a single flight of stairs. How much work does he do in walking up the 5-meter-high flight of stairs? How much work does he do when he walks down the flight of stairs? Now, I will say that for any instance where we have something that is traveling up or down, and I know that technically stairs, you do kind of move at an angle because you also move forward while you go up, and you also move forward while you go down. We only focus on, typically, the vertical aspect of the motion when it comes to stairs. Okay? I want you to think about this for a second, just like we did in our lab. So imagine you're standing at the bottom of a set of stairs. What do you physically have to do to get up onto the first step? can lift my leg, I can even, what do you need to do? It's not just putting the foot on there. You need to lift your own weight up to get up to that next step, don't you? Okay? Which is why in your lab I had you just take your weight and we use that as a force, because you need to lift with an equal amount of force to get your weight up. Okay? And that gets you up onto the next step. Then what do you do for the next step after that? Again, you lift your weight up. To get to the next step, you lift your weight up. So even though, okay, the weight is the downward directed force, okay, you are applying an equivalent amount of force to lift yourself up and carry yourself up those steps. Okay? So when we're going to calculate the amount of work done, okay, I'm just going to leave this as the FD cosine theta. Okay? I'm not going to designate that necessarily as an applied force or anything else. That's okay. But we do know that the force is equivalent to your weight. So we can just go ahead and plug in 80 kilograms for our force, correct? What do you mean no?
Good. You get it wrong.
Okay, Jack's right. You could do whatever your little heart desires. It's not necessarily going to be right. So what do we need to do to our 80 kilograms to get the force we need? Multiply by the acceleration due to gravity, multiplied by 9.8. So everybody in your calculators, 80 times 9.8 gives us... Someone lay it on me here. We get 784 newtons. Good is what that force should be. What is the displacement as we go up? It is 5. Okay? All multiplied by the cosine of. Let's think about this. You have to lift your weight up. You are going up. Again, I know that there's a horizontal component of that too, but that is different. Okay? So that ends up being the cosine of 0. Well, that ends up being pretty easy to do. 784 times 5 times what effectively is just 1 gives us a grand total of 3,920 joules. Okay, that's, I know this wasn't broken down to part A and part B, but I'm going to make it part A and part B. Now we want to know how much work does he do when he goes down the steps. And again, down is the one that always gives people headaches. I will have to admit, there are 2 different ways in which you can go down the stairs. One way is you can stand at the top of the stairs and someone can push you down the stairs. Your weight will then carry you down all of those steps as you go down. That's one way in which you can do it. There's another way, the preferred way of going downstairs. Okay? I want you to imagine now, if you're standing at the top step of the stairs, and you're going to go down to the next step, what do you need to do? One of the things you can do is you can have your weight carry you down those steps. That's scenario 1. But that's not the preferred way of going down steps. So imagine this. You have 2 feet firmly planted at the top step. What do you have to do? You have to lift your weight up to go down to the next step. Because you don't just sit there with your feet at the top of the step and try to push that foot forward and go to the next step, do you? Okay? You have to lift your weight up to get down to the next step. Then, lift your weight up to get down to the next step. So you still are applying a force in an upward direction equivalent to your weight. Oops, sorry. F D cosine theta. So we're still doing 784. Good. Now we're going down the steps. What are we going to put in for displacement? 5. It is the magnitude of the displacement. It is not assessing a direction. How do we take care of the fact that we're going down? With the angle. You are still applying forces to lift your weight in upward direction. What is the direction of your displacement? Downwards. So what is the angle here that we should be putting in? Cosine of 180 degrees. Therefore, you don't even have to use your calculators, because again, we should hopefully know our unit circle by now. Negative 3,920 joules. question was not asked of you, but you're all intelligent human beings. How much work did Mike do in total? 0 joules. For 2 reasons. 1, 3,920 joules on the way up, negative 3,920 joules on the way down. The sum is 0. And the other explanation is if we consider the entirety of the situation, displacement 0. Okay? So no work in total would be done. I know, again, that question was not asked in that sense, but it's what we get. All right, real quick, we're going to shuffle back to our note packet just for one slide. Then we're going to do one more sample problem, and in terms of notes and samples for today, that's going to be it. Okay, so good. A lot of stuff about work. Now, power. Power is easy. Okay? And truth be told, for the most part, it's exactly how you learn in physical science, for those of you that were here in the Grand Commonwealth of Virginia. Okay? Power is simply the rate at which work is done. We take a known quantity of work, we divide it by the amount of time it takes for that event to occur, and we can get a power rating. Mathematically, power can be found using the following equation. Power equals work divided by time. Where you might see it, and something that I need to start doing a little bit more is showing you the algebraic connection between things. Okay? Meaning, if we weren't just told there's 3,920 joules worth of work being done, but we need to figure out, hey, how much power? Could we just do FD cosine theta and substitute that in for work? Absolutely, that's all we're doing here. And for those of you that are starting to consider higher levels of physics as a potential, you need to make a living doing this. Okay? We do it all the time in terms of taking known algebraic equations, substituting into other quantities, so we can figure out a way to best represent what we have. Still, all of that divided by time. Okay? Power does have units of joules per second if we kind of use the derived unit because it is work divided by time. But we do also give this its own unit called the watt, abbreviated with a capital W. So this is where we have a little bit of the conundrum. In this equation, we have work as the variable represented as capital W with a unit of capital W. Okay? You know the difference between what a variable is and a unit is. We will not have an issue with it. Okay? Machines are commonly rated by their power. Okay? And I'm talking about things that do things mechanically. There's a little bit of a difference between this and electric power, and how it's derived at least. So that's kind of where we are. All right, let's do one last sample problem to kind of tie it up for us. And in the light of us doing our workout from last class, we have Ben Pumpeniron, who's elevating a 100-kilogram barbell up to 1.25 meter distance for a complete deadlift, which I know the picture's not showing a deadlift, in 3.8 seconds. What is Ben's power? You got it. Go for it. And Alyssa, I do appreciate you, when you are done, putting your solution up on the board. Okay, so Alyssa's response is kind of check what we have versus what she has. I would try to make sure we do parentheses around our entire numerator if we take the whole FD cosine theta as the numerator. All of that, okay, 980, wait, where did 980 come? 100 times? No, 9.8, we need to have the weight, we need to have the force, not just expressed as a mass. Okay, so 100 times 9.8 gives us 980, okay, up the 1.25 meter distance, and because we're applying a force in an upward direction and it's traveling upwards as well, the angle between those is 0 degrees, all divided by 3.8 seconds in one fell swoop. Gets us 322.368 watts. Does everybody agree with that? Okay, we should. I'm just trying to remember off the top of my head. I don't think you necessarily get a long string decimal number if you calculate work separate from that and then divide it by the 3.8. Just know that I kind of gave you some clean numbers this go around. We might have a little bit of difference in rounding error. It might not be a bad idea to do FD cosine theta divided by time if we have something that's a little less clean than what we have here. Okay? Any questions?